Continuing along with activity 4, the next part is using equation 16 with BE and alpha E from the NIST webbook to determine B0. It says for your molecule, but we're going to do all 3 of these molecules, HF, HCl, and CO. We'll do this in Excel. This won't be hopefully too painful. So BE and alpha E, we're going to go back to equation 16. Equation 16 says that the B sub V is equal to BE minus alpha E V plus a half. So if you want to solve for B0, you're just taking BE from NIST minus alpha E from NIST, 0 plus a half. So half times alpha E. BE and alpha E, those are equilibrium values, so you can determine B0, B1, B2, B3, etc. for the various vibrational states. It sort of tells you the rotational constant for each of the vibrational states for your molecule. And so then from there, we're going to use equation 12. This is our rotational energy as a function of J, but in wave numbers. So F of J is the rotational energy, but just in units of wave numbers. Of course, we could solve for rotational energies with equation 10. It's slightly more cumbersome because we have to go back to the bond length, get I, and then from there solve for the rotational energy. So it's going to be a lot easier just to really focus on equation 12. And then from there, we can get the rotational energy in wave numbers, and we can use our conversion factors in front of our packet here to convert energy to, say, kJs per mole. We can, of course, use Avogadro's number to go to joules, etc. Okay, so let's get over to Excel. We're going to be playing around with the same sort of temperatures here for our molecule. Now let's start with a generic rotational constant. Let's say we have a rotational constant of about 10 wave numbers. Of course, I'm not labeling here. You might want to label your spreadsheets, but this is just for demonstration. So what we might compare is our F of J. Well, we might make a table of J values and then a table of the rotational energy values as a function of our rotational constant. So of course we have 0, 1, 2, etc. So we're just going to take the previous cell, add 1, and we can copy this out. It says to do the first 50. Believe it or not, we're probably going to need even more than that. Probably not 186, but we might need a fair number. It's easy enough to delete later. Once we see the values we don't need. And then our rotational energy, just in terms of B0, would be B0 times J plus 1. So we're going to take our B value times the J value times the J value plus 1. Okay, now anytime you have a parentheses, make sure to put that multiplication sign in there. You really need it. If you don't have that multiplication sign, it turns out Excel is not smart enough, or at least some versions of Excel isn't smart enough to know that you just simply want to multiply there. Okay, so that should be 0. So the energy of the J equals 0 state is 0 in terms of the rotational energy. And then now we can't exactly copy down because the J value is copying down, like our rotational constant's copying. So we want to take the rotational constant, throw some dollar signs in front of the 7 and the A. That'll lock that value in. So as we copy down, that 10 value, the value of 10, will not change. So we're always doing 10 times the J value plus 1. So now we can copy down. And there's all kinds of tricks here in Excel. Like if you click the little corner here, then that'll copy down. You can drag it down accordingly. You can do all different kinds of tricks here. You can, of course, just copy and paste as well. And so these are rotational energies. These are in wave numbers. And then what I would do is just use the conversion factor from your handout to go to kJs per mole. So 1 kJ per mole is 83.5935. So if we take these values here and divide by 89.5935 wave numbers per kJ per mole, those will convert these quantities into kJs per mole. Here's another trick. I might copy here and then click here. If you use that little hand, whoops, that way. Okay, that's not doing the trick I thought it would do. Let's do it this way. Let's do a paste, scroll down, or excuse me, a copy, scroll down, and then a paste. So do a Control B. So you can see here that the J equals 1 level is about, and this is in kJs per mole. So this would be a rotational energy in kJs per mole. and you can see that in terms of kJs per mole, it's like a fraction to a reasonably large number. Something didn't paste right. Let me double check that we're doing this correctly. That looks right. Oh, they're just not showing up right. Okay, so then the other thing we might do is just get this in joules. Now this would be per single molecule instead of per mole. So this isn't joules per mole. This is just joules per single molecule. And so the conversion here is going to be, let's take the previous cell, and then we're going to say that there's 1,000 joules per kJ, so multiply by 1,000 joules, and then we need to say that there's, for every mole, there's an Avogadro's number of particles. So we need to divide by Avogadro's number. Hit enter, and we can copy down. I guess that was the trick I was trying to do earlier that I didn't work the first time I tried. But if you just have this little corner button, you can double click and it should paste all the way down the chart. Okay, now we really don't need these values. They're just maybe useful to see that in terms of a single molecule, the joules is relatively small, kJs per mole, fractions of a kJ per mole to a couple kJs per mole to larger. And then in terms of wave numbers, you know, j times j plus 1 times about 10 wave numbers for this example here, so it's going up accordingly. And you can see that each successive j value is even higher than the previous. So like each time we go up in j value, it goes to an even greater energy than the previous increase of energy was. So like the difference of your increase up by 20, up another 40, then we go up by 80, we go up by 100, etc. You can see that we're going up in a pattern. Okay, so now then our fraction in the jth state, so we're going to start with j equals 1. Obviously the fraction of j equals 0 compared to j0 would be 0. But what we need to do here is we need to account for the degeneracy, and the degeneracy would be 2 times j plus 1. So that's the g sub j for the jth state. Here the j equals 1 is what we're starting with. Dividing by the degeneracy of the j equals 1 level, well, there's only one way to have, dividing by the degeneracy of the j equals 0 level, which is just 1, there's only one way to have no rotational energy, so we're essentially just dividing all these by 1, and then multiplying by the exponential of the minus rotational energy, and then if we're doing it in wave numbers, that's easy, because then we'll just divide by the 695,035 wave numbers per Kelvin, and then times our temperature, and then we're going to put temperature, we're going to put some dollar signs to keep the temperature constant. And then add a couple parentheses. Oh, I basically hit enter without doing the parentheses. So then at 10 Kelvin, we have a, 17, well, this like of the molecules that are, we have a fraction j equals 1, it's about 16% of those in j equals 1. So we have like a reasonable fraction j equals 1, tiny fraction of molecules in j equals 2, and then essentially almost nothing in j equals 3, and then really nothing once we start getting up higher in rotational energy. And then the thing we can do is that, this is at 10 Kelvin, then we can do this at 100, 300, 1,000 and see how those fractions compare. So one of the things you might do to run this at, say, the 100 Kelvin temperature is to copy over here, and then all we really need to do is change the C7 as the 100. So we change the C7, changes the column to 100 Kelvin, and it gives us the fraction in the j equals 1 level. So we see for this hypothetical molecule with a rotational constant at 10 wave numbers, we see that there's a higher fraction in j equals 1 than j equals 0. So the higher energy state, even at just 100 Kelvin, has a greater population and a higher rotational energy level. And we can attribute that to the degeneracy. The fact that this degeneracy increases as the j value increases will allow these higher rotational energy levels, and also the fact that the rotational increase, the increase in energy for each subsequent increase in rotational energy level really isn't that high. allows some of these higher energy rotational states to become more populated than j equals 0, the ground rotational state. Okay, so obviously the fraction in j equals 1, if we did this math, it would just come out to be 1. So like the fraction of j0 compared to j0 is just unity, and then we see a higher fraction at 100 Kelvin. And you can go through this at 300 and 1,000, and you can plug in the more precise values for HF, HCl, and CO. They actually have a pretty interesting difference where HF has a larger rotational constant. I think it's around 20 wave numbers, and CO is particularly small. It's less than 2 wave numbers. You can get kind of a sense of how the rotational constant changes the populations in the higher energy rotational states. Okay, so I think that's all for this video. Hopefully this gives you a good introduction on how to use